In this exercise, we'll compute the average speed in a Maxwell-Boltzmann distribution of velocities. More generally, we'll just see how to compute an average for a continuous probability distribution. So, in this case, let's consider a fluid whose velocities are described by the Maxwell-Boltzmann distribution shown here. Now, generally speaking, you don't want to integrate this. You have to, but you don't want to, because the function is proportional to v squared times e to the something times v squared. That's complicated to integrate, generally speaking. In this particular case, we'll be able to do it by hand. Later on, we'll see a trick for estimating probabilities without having to do a full integral. The physical picture you should have in mind is a set of particles with their velocity vectors shown, but what this distribution function tells us is that actually there should be some smaller arrows and some bigger arrows. So I'm going to redraw the arrows now. And we don't have a statistically significant number of points here. Of course, I only drew 10 particles. But if you have 1,000 or 1,000,000 or 10 to the 23rd particles, then you can imagine that distribution function does a very good job of describing how many large velocities you have, how many small velocities you have. If we plot out the distribution function, then it'll look something like this as a function of speed. So the y-axis is the value of f, the x-axis is speed, where speed increases to the right. The first feature I would note is that, of course, there is a maximum probable speed, and that corresponds to the peak at the top of the curve, right? So there is some speed that is the single most probable speed. But you can also see from this that the average speed is probably not right there. Why do I say that? Well, the area under the curve represents a probability, and there's definitely more area to the right of that red vertical line than there is to the left. So I would guess, by eye at least, that the average speed is probably somewhere more over there. I didn't do a calculation to do that, I just moved the line. But we can do a calculation. We can actually compute what the average speed must be for this distribution. We'll do it in the same way that we would compute an average value for any continuous probability distribution function. So let's do that. The average value of the velocity, which I'll represent as v with a line over it, is equal to the integral from 0 to plus infinity of the variable v times the distribution function over dv. Just to be clear, if we hadn't multiplied by the variable v, we would just have the integral of f dv, and of course that equals 1. That's true for any normalized probability function, but in this case we're multiplying by that v, and that makes a big difference. So the first thing we'll do is insert the functional form of f, so we do that, and let's pull out some constants in front of the integral. Now I have the integral of v cubed times that exponential. The argument of that exponential is really complicated, so I'm going to do a substitution. I'm going to set a variable mu to be equal to the argument of the exponential. That gives us a d mu value. Now you have to be careful putting this stuff all back into the integral. The first thing that changes is one of the limits of integration, so now you can see we're going from 0 to minus infinity. That's because mu is proportional to minus v squared. So it doesn't change 0, but it does change positive infinity to minus infinity. Got to make sure you catch that. Next thing, this first term that I've circled there, that's actually v squared, written now in terms of mu. Why did I pick v squared instead of v cubed, which is in the original integral? Well, actually, we're going to cancel out 1 power of v. And you can see that if you look at this second term over here, that just comes from d mu equals minus mv over kt times dv, but that term contains a v. So that v canceled out 1 power of v in the v cubed. That's why I ended up substituting in for v squared. All right, assuming I did all that right, then we can move on and we'll get an integral of the form 0 to minus infinity mu e to the mu d mu. Now we've made a lot of progress, but we aren't quite done yet. The next step is to integrate by parts. And I left some room in the recording there in case everybody had to groan out loud. I hope you're okay now. What we want to do is to set mu equal to the x variable in an integration by parts. So remember how this works. If we choose x equal to mu, dx becomes d mu. That leaves dy equal to e to the mu d mu, meaning that y just equals the exponential function. That's the nice thing about the exponential. If you choose it for dy, then y is still just the exponential function. So now if we use this to integrate by parts, we get that our integral is equal to this. And just to be clear, this first term is the xy term up there in the integration by parts. You still have to evaluate it between the limits of integration, of course. The second term over here is just the integral of y dx with a minus sign out front. Okay, so now we can expand these things out and evaluate them at the limits of integration. It's still not trivial. This first term looks kind of complicated. We have to take the limit as mu goes to minus infinity of mu times e to the mu. If you think about this, though, it's not so bad. Which of these two functions grows more quickly? A linear function, mu, or an exponential function, e to the mu? You should have said exponential. If it grows more quickly, also shrinks more quickly if mu is going to minus infinity, that tells us that the whole term will go to 0 faster than it would go to minus infinity. Alright, that's good, so that first term I have circled now is 0. Second term is explicitly 0. Third term, well I didn't even circle it, its limit as mu goes to minus infinity of the exponential. We don't even have to make an argument about that, that'll clearly go to 0. So the only thing left is that very last term, minus the exponential of 0, which is minus 1, but then there's also a minus sign out front, so it becomes plus 1. Like all good calculus problems, we just did like 5 minutes of work and the answer was 1. Okay. So remember, that doesn't mean that the average speed is 1, that just means that the integral part of it is 1. We still have all those constants out front. So that's going to be our average speed. We'll simplify things by combining the terms in parentheses, and let's see if we can get this all under a square root, which I now do. So the average speed is the square root of the quantity 8 kT over pi m, where kb is the Boltzmann constant, T is the temperature, and m is the mass of a particle in this distribution. So as long as they all have the same mass and the same temperature, this will tell you immediately the average speed for any system described by a Maxwell-Boltzmann distribution.